The goal of this talk is to present a result that I worked on with Giuseppe Bargagnati on the bounded cohomology of this class of groups. Since I expect you not to be familiar with bounded cohomology nor with this class of groups, I will dedicate most of the time to introducing these two notions. In particular, I will give a brief introduction on bounded cohomology and on the instance of bounded cohomology we're interested in this case, which is the continuous bounded cohomology of groups. And so this is groups, sorry. Okay. And then I will define this class of groups that were introduced by Le Boudec in 2015, and they are a generalization of the maybe better known Burger-Moses groups. I don't know if you have heard of them. And finally, I will state the result and hopefully say something about the proof. Okay, so we start off with bounded cohomology. Okay, so bounded cohomology it's an invariant. It's an invariant for groups. It was introduced by Johnson and Trober in the 70s in the context of Banach algebras, and then it was developed by Gromov, who explored also its relation with simplicial volume. It is an invariant that you might find coming from different directions because it relates to many other invariants of spaces and of groups. For instance, it is related to simplicial volume, but it is also related to stable commutator length of groups. And in general, it is related to quasifications and stability. So, for example, there is a strong relation between the second bounded cohomology of groups and the quasimorphism of the group that we will briefly see. Okay, so we start with the definition, and I will give the algebraic definition for groups that is similar to the definition of the usual group cohomology that maybe you know, but is not needed to understand this. We start with G being a locally compact group. Can you see if I write like this? Okay, in case, tell me. Okay, GP is a group, locally compact group, and we denote with CBN the space of maps from G to the n+1 to R, such that F is continuous and bounded. Okay, so with continuous, of course, here we consider the product topology, and with bounded, we consider this with respect to the L infinity norm, so is equal to the supremum of the absolute values of the values of F for G in G to the n+1. Okay. Now, on these spaces, it works like this. Okay. So on these spaces, we have a G action that, once again, is the same that we have in the usual group cohomology. So G acts on CBN. Oh, sorry. Here I wanted to put G. Okay. I'm omitting the R. So I'm defining continuous bounded cohomology with real coefficients because it's the only one that we would be interested in today. In general, it can be defined for a larger class of coefficients. So we can substitute R with normed modules. But since we will only deal with real coefficients, I will omit it in the notation. Okay, so we have a G action on this space that is given by gf of g0 gn, where this is in G and this is in C, CB and G, is simply f of G to the minus 1 G0 G to the minus 1 Gn. Okay, and we denote with C, CB, N, G, and G above the subspace of G invariance. With respect to this action. Okay, now the last thing that we need to define is a boundary operator. So we have the following maps that we denote with delta n from C, CB, N, G to C, CB, N plus 1, G. And they are defined, okay, here we can also just consider the G invariance, but it works anyway. And we have the delta n of f computed in G0, Gn plus 1 is just the alternating sum of f evaluated at the tuples where we omit one of the coordinates at the time. So G0, Gi hat, Gn plus 1. With the hat, I'm denoting the coordinate that I'm omitting. Okay, so this gives us a cochain complex. We have a complex. So 0 goes to C, B, 0, G invariance, C, and so on, where here we have this boundary operator. And so the continuous bounded cohomology of G is just going to be the homology of this complex. So the continuous bounded cohomology of G with R coefficients is, we denote it with H, C, B, N, G, and it is the quotient of the kernel of delta n by the image of delta n minus 1. Okay. Now, let's see some properties. Oh my God. Okay. Bounded cohomology is in general very hard to compute, and it tends to vanish. So most of the non-results are vanishing results, while for the non-vanishing results, they tend to consist in computations for low degrees. So now I will tell you what happens in degree 0, 1, and 2, and then a little bit of vanishing results. So low degrees. Okay, so in degree 0, we have the same result that also holds for usual group cohomology. So the 0 continuous bounded cohomology of G is simply R for every G. While in degree 1, we have the first difference with respect to usual group cohomology. Indeed, we have that the first continuous bounded cohomology of G vanishes for every G. These results are both more general. They hold also with other coefficients, but I will not get into that. And the way in which one can show this is simply by doing the computation, and it is easier if instead of using the homogeneous chain complex, which is the one that I defined, we do the continuous bounded analog of the inhomogeneous chain complex. Okay, and for degree 2, I will not define this very well, but the idea is just that in degree 2, if G has a non-trivial quasimorphisms, maybe I should, okay, let's do this. Non-trivial quasimorphisms. Okay, then the second bounded cohomology of G does not vanish. Okay, this is just very rough, but just to say that the non-vanishing results for second bounded cohomology in general are obtained by finding non-trivial classes of quasimorphisms for the group G, where a quasimorphism is almost a morphism. Okay. Now, for the vanishing results, in this case, a very important role is played by amenable groups. They were already mentioned today, so I guess at least some people know the definition. I will not give the technical definition, but just so that everyone has an idea of what we're talking about when we talk about amenable groups. Amenable groups is a very large class of groups. They include finite and abelian groups, and all the groups that can be obtained by extensions, quotients, direct unions, and it's also a class that is closed under taking subgroups. So, and these ones that are created in this way are called elementary amenable groups. So it includes also other groups, and yeah, so it's a very large class of groups. And the reason why it is related, is strongly related to bounded cohomology, is, for instance, this theorem by Johnson. It's a characterization of amenability. And it states that if gamma, let's say that in this case we consider a discrete group, gamma is amenable if and only if its bounded cohomology vanishes. Oh, here I want to use coefficients. Vanishes for every degree greater or equal than 1, and for every coefficient module V that is dual. Okay, even though I didn't give the definition for a coefficient, I still wanted to give this result because it is one of the major results of this theory, but also because it shows one other important aspect of bounded cohomology, which is that coefficients really do matter. Having vanishing results for different classes of coefficients make a difference. In fact, we have an analog of this result that characterizes finite groups. Yes? Oh, I'm so sorry. Yeah, sorry, because I'm used to writing G when the group is topological and gamma when it's a discrete group, but yeah, then I forgot. Sorry, thank you. So we have the analog characterization for finite groups. And in this case, we have that gamma is finite if and only if its bounded cohomology vanishes for every n greater or equal than 1 and for every v Banach module. So what we see from here is that by allowing a larger class of coefficients for the vanishing result, we obtain a smaller class of groups that are characterized by this property. And in general, one direction of research in bounded cohomology is whether there are other algebraic properties of groups that can be linked or even characterized by vanishing results of bounded cohomology for certain classes of groups. Okay. Then I think, yes. Uh, is if gamma is finite, then any function is going to be bounded. Yes. Yeah. In fact, this result also holds for the usual group cohomology, right? It also vanishes for finite groups. And this is use. Yeah. Yeah. Okay. Lastly, uh, one last thing that I want to say in this introduction of bounded cohomology, it's a way of computing bounded cohomology for using different resolutions. So as I was saying, it's in general hard to do computations of bounded cohomology. And one way of circumventing this problem is by using different resolutions, and in particular, uh, using amenable resolutions. What do we mean? So we have the following theorem. Also, this can be generalized, but I will state it in the most simple way possible. If G acts on a set S, this is a countable set. With amenable stabilizers. Then this resolution isomorphically computes the bounded cohomology of G. Okay, so this is a way that we have of computing bounded cohomology, and in particular, through this kind of resolutions, we find some of the best known vanishing results for bounded cohomology, which is by finding spaces on which the group acts amenably, and hence finding other resolutions with which we can compute the bounded cohomology. Yes. Oh, I'm so sorry. Yeah, thank you. Yeah, and the boundary operator is the same as before, and also the action. Okay, I think I will move on to the second part of definitions that I that will be given today. I'm sorry for the amount of definitions in this talk. So we move to groups. With almost prescribed. Okay, I will not write it again. APLA. Okay, so now the groups that we're interested in today are these groups acting on trees with almost prescribed local actions. These are groups that were introduced by Adrienne Libudek in 2015. And since their introduction, they served as examples of many algebraic properties of groups. For instance, they served as the first example of a C-star simple group with non-trivial amenable radical. I don't know if you know this. I don't, but it was a long-standing open question, so that is interesting. And in general, they allow a lot of freedom of choices, and for this reason, they provide a number of examples. And as I mentioned before, they're a generalization of the Burger-Moses groups, and I will first give the definition of the Burger-Moses groups. But in order to go into this, we need some notation. So these groups are groups of automorphisms of the tree, on which we require some so they're automorphisms of the tree, but we do not allow any possible permutation of the edges around each vertex. So we want to have a notion of the local permutation around each vertex. So we want to have some control on where each edge is sent. So we want to have a color tree. So from now on, T is a regular tree of degree D greater or equal than 3. This is pretty standard, but we denote with ET the edges, with VT the vertices, and with E V, small v, for V in V, the edges containing V. Okay, we want to define a coloring on this tree. And we also denote with omega just the set of the elements. And with sim omega, the symmetric group. Okay. Okay, one last thing, just so we're clear with everything. With out T, we denote the group of automorphisms of T. And we consider this as a topological group with the pointwise convergence topology. And with this topology, it is locally compact. Okay. Yes. Sorry. I mean that around each vertex, we want to have the same number of edges, and this is the regularity. And the number of edges is the degree. So in this case, I would have the edges around each vertex. Sorry? Yeah, that is just that a sequence of functions converges if it converges in each point. Yes?
No, the elements, because we have an omega for every vertex.
Yes, is the same omega because we have always the same number of edges around each vertex. So it's like we want to. The idea is that we want to associate a color to every edge around each vertex. Okay. Okay, so coloring. I don't know if you want the well. So we want to give a coloring, sorry, on this tree, and so we, which is a map from the edges of T to omega, such that the restriction that we denote with CV that goes from the edges containing V to omega is a bijection for every V in V. Okay? Now, as I was saying, we want to have some control on the color to which a colored edge is sent via an automorphism. So in order to do this, we give the definition of a local permutation. So the local permutation of G at a vertex V. This is an element of out T. Is we denote it with sigma G V, and it is the composition of CV to the minus 1 with GV with CGV. What do we mean with this? So this is just the restriction. I'm using basically the same notation as here. We restrict the automorphism G to the edges containing V. So this is GV goes from the edges containing V to the edges containing GV, and is restriction of G. And I claim that this is an element of the symmetric group of omega. Let's see if we agree on this. So we start from CV to the minus 1. What does CV do? It is a bijection, so we're allowed to do to take the inverse. And so what we mean is that we start from a color and we take it back to an edge containing V. Then through this restriction of G, we send the edge containing V to an edge containing GV, and then via CGV, we send the edge to the edge containing GV to a color. Okay, so let's see an example of these local permutations so that we are clear. Yes? No, this I should have said. T, on T, we're considering simplicial actions. So we can just identify the actions with the actions on the vertices. So we're not considering, I mean, yeah, we don't need that, yes. Okay, where was I? Here, so example. Just a quick example of the local permutation, because I think the definition makes it sound much harder than what it actually is. So let's say that we have 3 vertices, V0, V1, and V2, and let's say that they're sent to, so this tree continues. I'm just taking like a part of the tree. No, in every direction. And they're sent to G V0, G V1, G V2, and say that here we have the colors 1, 2, 3, 4, and here I had 1, 3, 4, 2, 3, 4, and here 1, 2, 3, 4, 3, 1, 4, 1, 2, 4. Okay, I don't know if you see the numbers. The weird one is a 4. So which are the local permutations here? So for the first, sigma G of V0, what is it going to be? Well, this map G is sending the color 1 to the color 1, 2 to 2, 3 to 3, and 4 to 4. So here the local permutation is simply the identity. For the second vertex, we are sending 2 to 2, 3 to 1, 1 to 3, and 4 to 4. So here we have the transposition 1, 3. And finally, in V2, we're sending 1 to 3, 3 to 1, 2 to 4, and 4 to 2. So here we have the two transpositions, 1, 3, and 2, 4. Okay? Okay. Nice. So I think we have everything that we need to define the Burger-Moses groups. I will try to bring this down. Okay, now let F be a subgroup of the symmetric group of omega. We define the universal Burger-Moses group relative to F as, not as, okay, is UF, the group consisting of all the automorphisms T, of T, where the local permutation at V is contained in F for every V in V. Okay, so what we are requiring is that every automorphism that is contained in this group allows only local permutations that are contained in F. So let's see what this brings us. For example, with the example that we gave before, if we have U of the group generated by just this transposition, then the G of above is not contained in this Burger-Moses group. Do you agree? Right? Because as we saw here, this local permutation is not included in DF in this case, okay? So some remarks that I want to say on these groups is that UF is closed in out T. And so in particular, we take it with the subspace topology. And with this topology, it is locally compact. I'm stressing the fact that everything is locally compact because we need it for bounded cohomology. So that's why we mention it. And moreover, we have the case of UID. So this is the universal Burger-Moses group where basically we're not allowed to permutate any of the edges. We're just like moving very in a very fixed way. And for this group acts on the tree transitively. And is not amenable. Why am I interested in this? Well, because the universal Burger-Moses group associated to just the identity is contained in every other Burger-Moses group, right? Because whenever we have F subgroup of F prime, then UF is a subgroup of UF prime, okay? So in particular, UID is contained in every universal Burger-Moses group. And so this implies that every universal Burger-Moses group acts transitively on the tree, and every universal Burger-Moses group is not amenable, as we said, amenability is closed undertaking subspaces. So if we have a non-amenable subspace, a non-amenable subgroup, then the original group was not amenable. Can I erase this? I don't remember. Okay, we're almost done with the definition. We just need the last one. Then we're free. Okay. Now we consider F to be a subgroup of F prime, which is a subgroup of the symmetric group, and we require F prime to preserve the orbits of F, the orbits of F with respect to the action on omega. Okay, then. Okay, so this is group acting on T with APLA. We define the group acting on T with almost prescribed local action, G, sorry, this is a U, GF F prime, as the group consisting of all the automorphisms of T, for which the local permutation of G at V is in F for all but finitely many vertices, and the local permutation is in F prime for every V in Vt. Okay, so what does this mean? It simply means that we're basically in the same situation as for the universal Burger-Moses group, but for a finite number of vertices, we allow more freedom, and we allow the freedom that is contained in F prime, that is a larger group. Okay, so some remarks. Well, UF is a subgroup of GF F prime, which is a subgroup of UF prime. This comes from the definition. Then these groups are not closed subgroups. They are, in fact, dense subgroups of these closed subgroups. And we endow them not with the subspace topology. And this, I mean, the natural topology on these groups is the one let's say it, with the topology that makes the inclusion UF in GF F prime continuous and open. Okay, so far everything comes from Le Boudec. I need to change Blackboard. Oh. Okay, I don't have a lot of time left, so maybe I will get to the result. Okay, with this topology, these groups are locally compact. So we can compute their bounded cohomology. And one last thing is that the stabilizers of GF F prime are amenable. So the stabilizers of the action of GFF prime on T, on the tree. Okay, and this is relevant information because of what I said before of the fact that we can compute bounded cohomology using other resolutions when we have an action with amenable stabilizers. So this is behind the proof of the statement that I will now finally give. So the theorem by Bargagnati and myself is the following. So as before, we have F, a subgroup of F prime, which is a subgroup of the symmetric group of omega, and F prime preserves orbits of F. Then we have two options. One, if F prime acts on omega two transitively, then the bounded cohomology of G F F prime vanishes for every n greater or equal than 1. The second option is otherwise. Is there an H? Well, no. Wise. Okay, otherwise the second bounded cohomology of this group is infinite dimensional. Okay, so we have a complete characterization of whether or not the bounded cohomology of these groups vanishes, and the key is the two transitivity of the action of the bigger group on omega. By two transitivity, we mean transitivity on the couples. Okay, now in the last few minutes, I will say something about the proof of this result, and in particular, what I want to mention is why this two transitivity appears and how we use it. Okay. Okay, so remark. We for the proof of this statement, we want to be able to send finite geodesic segments to finite geodesic segments, and this is where the two transitivity appears. Why? So if we have a finite geodesic segment in T, say V0, V1, V2, and with some color C1, C2, and we want to send it to some other finite geodesic segment, say V0 prime, V1 prime, V2 prime, with some other color C1 prime, C2 prime. Then, what do we need? Well, we know that all these groups act transitively on the vertices because they all contain U id, which acts transitively. And so we can send V1 to V1 prime, right? So we can do this. Now, since we have the two transitivity of f prime, and we are allowed to use permutations, local permutations that are contained in f prime for a finite number of vertices, we can use the permutations in f prime for this vertex, okay? So this gives us the fact that we are allowed to send the couple C1, C2 to the couple C1 prime, C2 prime, okay? And this also sends V0 to V0 prime and V2 to V2 prime, okay? So this is how we send finite segments to finite segments. Now, this is not completely done because we want to extend this automorphism to the entire tree. And this a priori, it's not always possible, but in this case it is possible because we know that f prime preserves the orbits of f. So since f prime acts too transitively, in particular it acts transitively, and so f has only one orbit, so it acts transitively. So what does this mean? It means that for V0, say that we are using here the permutations in F, then we can send C1 to C1 prime, and then we don't have any control on when of the color of the other edges, but that is okay, right? And so we extend it to the vertices, to the edges neighboring V0. And then we continue this way, always using the transitivity on each vertex to make it compatible with the automorphism that we had partially defined before. Okay, so this is a little bit of the idea of why this two transitivity appears. Now I will be even more hand wavy. Why is this useful? So for this first part, idea of item 1, for this first part, what we want to use is we want to find a resolution to compute the bounded cohomology of GFF prime that we can relate to another resolution that computes the bounded cohomology of a group that we know is amenable. So what is the resolution that we use? We use the aligned, I think it's just one L, I don't know, align complex, which was introduced by Boucher and Monod in, I think, 24, which basically consists in the very, very roughly, it is the dual of the R module generated by the aligned n tuples in T to the n. So this is why we're interested in being able to send finite aligned tuples to finite aligned tuples. And the other resolution that we want to use to find this connection to is the resolution computing the bounded cohomology of the setwise stabilizer of a geodesic line. And so in this case, the fact that geodesic lines have amenable set stabilizer. So at the end, what we obtain is the following. So we have this aligned complex that I didn't really define, but you can believe me, that is based on taking finite aligned tuples in t to the n. And so we have this aligned complex that we denote in this way. And we take the invariance as usual. And so the chain complex associated to this computes the continuous bounded cohomology of GFF prime. And we are able to find an isomorphism from these spaces to L infinity, in this case alternating, of L to the n plus 1 RH, where this is the setwise stabilizer of L. So we're able to find a geodesic line L for which the setwise stabilizer H is amenable, and for which this map from this resolution of GFF prime to this resolution of H is an isomorphism, so it is injective and surjective. And for the injectivity part, we use the fact that we're able to send all the finite geodesic segments that are in here to finite geodesic segments in the line. I'm sorry, this was very hand wavy. And then for the second part, so the non-vanishing of the second bounded cohomology. Okay, here we use item 2. Here we use a result by Iozzi, Pagliantini, and Sisto. That I state only for this context. We had to change it slightly, but it's more or less this. So in this context, one of the following holds. And the three options are G, F, F prime fixes a point at the boundary of T. 2, G, F, F prime acts transitively on geodesic segments on finite. And number 3, HCB2 of G, F, F prime is infinite dimensional. Okay, so what do we do here? Well, here we are able to rule out option 1 and 2. We're able to rule out option 1 because we checked that G id, so G where the, sorry, U id, which is also G id, whatever, does not fix a point at the boundary. And so since it is contained, once again, in all of these groups, they also don't fix a point at the boundary. So this is not the option that appears in our case. Number 2, once again, we do not have the two transitivity of F prime because we are in the otherwise case. And we showed that in order to have transitivity on finite geodesic segments, we need to have two transitivity of F prime. And so this option also does not hold in our case. And so we're left with the infinite dimensionality of the second bounded cohomology. Here, the proof of this part uses quasi-morphisms, and in particular, what they do in the proof, and what we had to do in our context is finding infinite linearly independent classes of quasi-morphisms, of non-trivial quasi-morphisms for these groups. And these happen to be the so-called median quasi-morphisms. And this is everything I wanted to say. Thank you.
Well, thank you, Elena. I've been told we better use the microphone. So if anybody's got questions, bring it to you. Yeah, I know, me also.
Thanks. What all the things you said are based on some subgroups of automorphism of trees.
Mm-hmm.
Do you know if you can do something similar for graphs of positive genus?
I don't know. I don't know. I didn't think about this question because, like, yeah, all the definitions did not come from us, so we used these groups that were already defined. But maybe that is an interesting question. I don't know. Mm. Yeah. Yeah, I don't know. I have to think about where we use the fact that these are actually trees. I fear we do use it, but it doesn't come to my mind. Yeah. Yeah, that's I don't know, like the compatibility of the colors. Yeah, maybe. Yeah, it would be a problem. Yeah.
Okay, wait. Yeah, I see.
I mean, bounded cohomology doesn't behave very well for subgroups, so I don't know. I don't think so. Yeah. Yeah, I mean, if you can still like use the hypothesis of this for subgroups, then yes, but like there is no obvious like thing that goes to bounded cohomology of subgroups. So I don't know. I would need to be specific to some classes of subgroups. I fear. Yeah.
If we don't have any other question, let's thank Elena again. Okay, we are ready to resume for the contributed talk session. Biplab Basak from the Indian Institute of Technology. He will talk us about characterization of normal 3 pseudomanifolds with small g2. Thank you.
Thank you. Good afternoon, everyone. So I am Biplab from IIT Delhi. So at first, I would like to thank the organizer for giving me this opportunity to come here again. So I last and the first, basically, not the previous, and my first visit was in 2015 February. So I still remember. So I gave, I think, talk here only. And now after more than 10 years, I am here and attending this one. So yeah, so that is very good experience actually. So here, this is my talk. So basically today in this talk, we will characterize that normal 3 pseudomanifold with small g2. Actually, we start with some basic definitions. One might feel a little bit bored because of the too many definitions, because I thought maybe we should include all the definitions, because this topic might be new for someone, right? So first of all, we start with that abstract simplicial complex. So a set family is called an abstract simplicial complex if for every set X, if we take any non-empty subset of X, then that Y should be in the collection delta. And then if we take a collection of simplices, then it is called a simplicial complex if the collection of the vertex sets of that simplices is actually an abstract simplicial complex. And then if we have a simplicial complex, then we can define these two terms, that one is link, another one is star. So link of an I simplex is basically collection of all the simplices such that intersect does not intersect with that previous simplex sigma, and their union should be in K in that collection. And if we know the link, then if we take that every element of that link, and if we take again that union with the sigma, then that will be, that collection is again a simplicial complex, and that is called a star. So basically topologically, link will have a, if we have a small point, then link will be basically, if we take a closed neighborhood and then that bounded of that closed neighborhood, and a star is basically just that closed neighborhood. That's it. So if we have a simplicial complex, then we can define a geometric carrier of that. So that's mean if we just take that union of those simplices in some Rn, and if we take the subspace topology, then that will be a topological space. So that is called a geometric carrier of K. And if we have a PL homeomorphism from that K with a M, then we say that K, that is simplicial complex, is a triangulation of the manifold M. So again, as I told you, the long definitions. So now we define that normal 3 pseudo-manifold. So there is a term pseudo-manifold and then normal pseudo-manifold. But here I just that exclude the notation. So I just define for the 3-dimensional cases only. So a simplicial complex, a 3-dimensional simplicial complex is called a normal 3 pseudo-manifold if link of every vertex is a triangulation of a close connected surface. Now, if the link of every vertex is a triangulation of a sphere, then the normal pseudo-manifold is actually a manifold. And if the link is not a sphere, we call that vertex as a singular vertex. So therefore, you can basically say that manifold is nothing but a normal pseudo-manifold with no singular vertices. Now, if we have a simplicial complex K, then we can count that number of vertices, number of edges, and F0, F1, F2, like that. And if I basically denote the number of the I simplices of that collection K. And then if we have only that number of vertices and number of edges, then we can define this term G2, which is by this one for any D simplicial complexes. And one can check if we have just a close connected surface, then this term G2 is just the 3 times the Betti number. So that's mean any close connected surface is uniquely determined by the basically that G2. Right. So now the questions come from here. So if we restrict that G2 and if we increase our class, that increase the dimension, say 3 dimension, 4 dimension, and if you have a limited information, only G2, that's mean only the relation between vertex and edge. Then what can be those manifolds or pseudo manifolds? So here we will classify basically normal 3 pseudo manifold with respect to that term G2. So as you can see that for sphere, G2 is 0. That's mean if you take any triangulation of sphere, that is unique. So that is, triangulation is not unique, that number is unique. It is, you always get 0. If you take any triangulation of RP2, it always give that G2 is 3. If you take any torus or clean bottle, then G2 of the triangulation will be 6. As it is the 3 times the Betti number. That's it. So now first question is, so why we are taking that G2, right? So there are many relations. If we have a vertex set of vertices and edges, so there are many relations are there. So why we are interested to particular this G2? That is because it has important relation with the rigidity theory. So rigidity theory says, first of all, that we first define that what is an embedding. So a de-embedding of a graph is just an injective map from the graph to some RD. And then a graph, basically the embedding of the graph is called rigid. If we push that graph a little bit, then whole structure move together. So that's mean there is an epsilon such that whenever, for any embedding G, if that is very close to F in terms of vertices, and if we have the same edge length, then basically that distance between any two vertices will be the same. So basically this means that basically if we have a structure of a graph, if we push that graph a little bit, then whole structure move together. Now a graph is called a generically de-rigid if the set of all the de-embedding of G of the graph F is an open and dense subset of the set of all de-embedding. And then whenever we have a rigid, generically de-rigid graph, then we can define the stress function for that graph, and it is defined by this way. Now you can check that if we just take this 0, then automatically it follows that this equation follows, right? So that's mean one can check easily. So this collection forms a vector space, and this vector space is called a trace space. Now that was the beautiful result by basically Kalai, I did not mention here. So it was proved that this dimension of this trace space is basically that G2. So here from these results, basically we have a relation between that G2 and this rigidity one. So since we are talking about the rigidity for any graph, so how we actually define it is for a simplicial complex. So for a simplicial complex, we just take that edge graph. So that's mean that one skeleton, that's it. And if that graph is rigid, then we will say that our simplicial complex is rigid. Now recently in 2008 and 9, so Schwartz basically works on PLD manifolds with respect to G2. So he has given basically many kind of classification results on G2. And much before that, in 1980, Stanley proved that G2 is bigger or equal to 0 for any simplicial D polytope. And there are some more results. So basically, Kalai proved that for a normal 3-Schwider manifold, G2 of K is always bigger or equal to G2 of link of V. Here he used that rigidity theory. And basically from now this, we have already proved that, we have already seen that G2 of link V, that is always bigger or equal to 0, right? So that's mean G2 of K is always bigger or equal to 0 for any normal 3-Schwider manifold. So in basically 1980, Stanley proved it. It is for any simplicial D polytope, and later it has been extended for the normal 3-Schwider manifold. Then after that people realized, okay, then we can study normal 3-Schwider manifold in terms of G2. So we can think about that classification, combinatorial as well as topological. So again, much before that, in 1970, Warkapt proved that K, if K represents a 3 manifold and G2 is less or equal to 9, then K is a triangulation of a 3 sphere. Moreover, if G2 of K is 0, then K is a stack sphere. So actually when he proved these results, so that time G2 was not introduced. So he just took that relation, and later people realized that that relations basically gives you G2. So the G2 mentioned actually, defined in 1980, but much before that, Warkup proved the similar results. So what is a stack sphere? So stack sphere is very important in this talk basically. So stack sphere means if we can start with any boundary of a D+1 simplex. So that is a D sphere, time version of a D sphere. Then we can take that feature subdivision. So in other words, what we can take some number of D+1 simplices and stack them together like that randomly. There is no kind of algorithm or any pattern. So you can just stack them randomly. Then we have some kind of a D+1 ball again. Take the boundary of the D+1 ball, that is called a stacked D sphere. Okay, so now recently, basically, so we have already seen that G2 is 0. Also, if G2 is 0, then we know this is taxpayer by Kalai. Then in 2011, Nevo and Novinsky classified all normal 3 pseudo manifold when G2 is 1, and then classified for G2 is 2. And all of these cases, K is a triangulation of a D sphere. And so from there, we have basically one question is that if we have something, so they have given basically that combinatorial characterizations of those pairs, how those pairs comes basically. So now if G2 is 3, then we realize that, okay, so there might be some kind of singularity, because now there is a singularity, there is option, because then singularity will be just RP2, since G2 of RP2 is just 3. So there might have some kind of singularity. And we don't know how many numbers are there, how many RP2 can be there. So now we prove basically that if G2 is 3, then we prove that the number of RP2 will be exactly 2. And we prove that then geometric carrier of K is either sphere or suspension of RP2. So what is suspension of RP2 topologically? So one can think like that. Sorry for that bad picture. So we can take a RP2, take product with 0, 1. Then this we will have a 3 manifold with 2 boundary components, and just count of the boundary components. So it will give you a basically suspension of RP2. That is topological concept. We will have a combinatorial concept as well. It is called a one vertex suspension. It says you take a triangulation of a RP2. This is a triangulation of a RP2. Now just choose a vertex and remove it. Okay, so now we have this portion is hollow and we have some kind of pink portions. Now we put one edge inside of this hollow thing, and then we take kind of a join. I did not define that term with this. So that's when we will construct 3 simplices like that. If UV is my edge, then UV 1, 2, UV 2, 3, UV 4, 3, 4, UV 4, 5. So these are my 3 simplices, extra 3 simplices. And then we just take this pink region and cone off by the U and V both. So that's mean we will have some kind of this structure. Okay, so this is called basically one vertex suspension of RP2. Now one can check this one vertex suspension is basically a triangulation of the previous suspension. So one can check by just take a vertex between 6 and 7 and do some kind of Barycentric subdivision, and then one can easily prove it. So that is simple thing. Okay, so now there are the 2 combinatorial operations. One is Handel addition and connected sum. So this means basically, so you don't need to read that. There's too many things written there. So basically what we'll be doing, so to define, first of all, that Handel addition, what we'll do, I have a picture. So just take 2 triangles, those who has basically done sufficient distance. That's mean if we identify this vertex with this vertex, then their distance should be at least 3. So that's it. So now if we can find this kind of 2 triangles such that number of distance between the number of vertices is at least 3, then we can just identify those 2 triangles. Then topologically we will get this kind of picture. So this is called the Handel addition. And connected sum means like if we do the same thing for the 2 different objects, 2 disjoint objects. So if we have a triangulation of some manifold M, triangulation of something, it may not be manifold. If we remove one triangle here, remove one triangle here, and then join them. Basically, if we remove one D simplex and D simplex here, if it is D-dimensional, then we just identify the D minus 1 that ball. Okay, so now it is known that if K is a normal 3 pseudo manifold and it has a missing tetrahedron means that tau is not in K, but all of its boundary will be in K. Okay, so that's means all of its space will be in K. And if we have a missing tetrahedron, and that missing tetrahedron has a property that link of every vertex of that tau is separated by the remaining actually cycle. If we have a missing tetrahedron, say in dimension 3, then if we take the link of a vertex will be just a cycle. right? So if we remove basically that x, so basically it says that link of x for any vertex, it is separated by the link by that other the missing triangle formed by the other three vertices. Now if that is true, then k is obtained by a connected sum or a handle addition. That is a standard result. Okay. Now there is another term called edge folding. So it is kind of similar thing. So this is not new. So we define that basically. So it is similar kind of handle addition only. So it says that if we have a say normal d-dimensional simplicial complex, no need of taking that normal three-shooter manifold. And if we have two simplices, two d-simplices, and one edge is common, then what we'll do, we can just remove those two d-simplices and then join their identify their boundary. Then we will have a new object. So that is called basically that edge folding. And the reverse one is called the edge unfolding. So if we get that object this one, then we say that this is edge folding of k, and we say that k is edge unfolding of this. So why we are doing that one? So if we do that edge folding, then G2 is increased by basically D choose 2. So in dimension 3, it increased by 3. So this we proved. So we proved that if K is a normal 3-shooter manifold with G2 is lesser or equal to 2, then K is a triangulation of a 3-sphere and is obtained from some boundary complexes of 4 simplices by a sequence of operations called that connected sum and X expansion. So only using these two operations, one can get this K. So we give this kind of combinatorial structure. Similarly, we just rewrite the proof of walk-up as well. So if we prove that if K is a manifold, 3 manifold, and if G2 is lesser or equal to 9, and then we work prove that it is a triangulation of a 3-sphere, but we proved that basically it is obtained from some boundary complexes of 4 simplices by a sequence of combinatorial operations. So I just removed those combinatorial operations because again, otherwise I have to add those definitions. And there is another one. So we proved that if K is a normal 3-shooter manifolds and G2 is lesser or equal to 4, then K will have either no singular vertices or exactly 2 singular vertices. So that was the main results basically. So if there is no singular vertex, then it is a manifold, and we proved that in that actually we then from this result, that is a walk-up, we can give a combinatorial structure for that one. But if it has 2 singular vertices, then we prove that basically it is a suspension of RP2. So here is the proof basically. So this is the outline of the proof. So if K is a normal 3-shooter manifold with G2 lesser or equal to 4, and which is not a sphere, then K is obtained from some boundary complex of 4 simplices by a sequence of operations of type that connected sum, X expansion, and edge folding. So that's it. So with these 3 operations, and edge folding will be applied only once. So there are 3 cases we have to study. So first case is there is no missing tetrahedron in K. If there is no missing tetrahedron in K, then we prove that so there will be an edge which edge can be contracted. So therefore G2 will be reduced by 1, and new G2 will be 3. And since G2 of link of a vertex is already 3, so another X contraction is not possible. So therefore now this new K1 must have a missing tetrahedron. And so we can proceed to case 2. So case 2 means, so K have a missing tetrahedron with the property that every vertex of Kx, every vertex X of sigma is basically separated. Link of every vertex X is separated. So in that case, we by the previous results, we know it is either a handle addition or a connected sum. But handle addition is not possible because if we do the handle addition, then G2 is increased by 10, which is not possible because our G2 is lesser or equal to 4. So only possibility is connected sum. Now if it is connected sum of this one, and if K1 contains one singular vertex, then K1 should contain the other singular vertex as well, because our singularity is RP2. And there is no normal 3-shooter manifold with exactly one singular vertex, which is RP2. And if K1 contains both singular vertices, then K2 and other one is basically a manifold. There is no singular vertices, and G2 will be less or equal to 1. And in that case, we already know the classification of that one. And also for this one, right, fine. So in this case, basically, we can have this kind of classification, right? Now the other case is K has a missing tetrahedron such that link of U is not separated. So link of one vertex is not separated. In that case, we proved that. So link of there will be another vertex where V such that UV should be an edge should be there, and link of V is also not separated. And in that case, we proved that K is obtained by the edge unfolding only. And again, then G2 will be reduced by 3. So K is obtained by edge folding. So K dash is obtained from K by edge unfolding. So G2 will be reduced by 3. So it will be then less or equal to 1. Then we know the classification. Now the other case is K have a missing tetrahedron where link of U is not separated. There will be only one vertex where link of U is not separated. And actually this case is not possible. So these are all basically cases. And there is another one that again this is the outline only, that if K is a normal three-shooter manifold, then K is a triangulation of either sphere or suspension of perpetuum. If K has no singular vertices, then it is follows from the workup result. If it has two singular vertices, then when we do that edge unfolding, we do this one only. So basically what we did, we first take a 3 ball, we choose 2 region for that one, that is 2D ball, which shares a common vertex. Then we identify those 2 regions with reverse orientation. Basically we are constructing one Mobius strip only, and then we just do the boundary cone down. That is basically the boundary collapsed, and it will give you a suspension of perpetuum. So that's all. These are the references. Thank you.
And do we have any rapid question? Please.
So are there infinitely many pseudo manifolds of, say, G2 is 4?
For G2?
G2 is 4.
4. Oh, no.
4.
So if you take G2 is 4, then yeah, so basically you can have infinitely many, but basically it is that I define that one vertex suspension of perpetuum, that object, and the facet subdivision of that one, and edge expansion only.
All right.
So you can one can construct infinitely many,
Mhm.
but topologically they are same.
Mhm.
So if you take as a topological object, then all of them are homeomorphic.
Okay, thank you.
Any other? Okay. We thank Biplab again.
Okay, thank you.
We are ready to restart with Julian Bruggerman from the INPAM, who will talk us about the on spaces of discrete and smooth Morse function. Thank you.
Okay. Hello, everyone. Thanks to the organizers for giving me the opportunity to speak here. And since it's already a little bit later in the day, allow me to refresh all of us with 2 inspirational quotes. The first of them is maybe not so unknown to mathematicians. Every mathematician has a secret weapon, mine is Morse theory by Raoul Bott. And the second one is, if you know the enemy and you know yourself, you need not fear the result of 100 battles from the book The Art of War. And in this talk, I will interpret this in the following way. If we know the tasks that we want to solve, which is kind of like our enemy, because we have our secret weapon, and we know ourselves, like we know our techniques, then we can basically write 100 papers. Okay, so what's the plan for today? For this talk, in the beginning, I will give a very short recapture of what Morse theory is. I will not give any details, but I will rather give the general feeling. Then I will talk a little bit about the space of Morse functions, which is also known under the name Cerf theory. Then I will talk about discrete Morse functions. There I will give a little bit more detail. And I will briefly hint at how they may appear in topological data analysis. And then I will talk about the space of discrete Morse functions. And in the very end, I will say a little bit about is there a notion of discrete Serf theory, and what does that look like? Okay, so what's Morse theory? So basically, we want to study manifolds by using certain well-behaved smooth functions from the manifold to the real numbers. And what do we want to do? Well, we want to induce some filtration on the manifold, a sublevel filtration. We want to find critical points of the function and gradient flow lines between them. And these techniques will give us a combinatorial decomposition of the manifold at hand. And then we can use this decomposition to efficiently compute topological invariants and to analyze, for example, the homotopy type or also other information of this manifold. Okay, so if we have a torus and take some projection in this weird direction, then we have a minimum somewhere, we have two saddle points, we have a maximum. And the thing we observe is that if we take sublevel sets around the minimum, then everything looks like a point. And only by passing the other critical points, our topology actually changes. So once we pass the first saddle, we have one circle. Once we pass the second saddle, it's homotopy equivalent to two circles. And once we pass the maximum, we get our torus. And well, the question is, what kind of enemies do we want to defeat? What kind of problems do we want to solve? And I'm very lucky today because I do not need to introduce this theorem too much because we already saw it in the first talk. There is the H-cobordism theorem, which gives us a criterion for when a certain cobordism is actually isomorphic in whatever category you like. A category of manifolds like smooth topological PL, there are different versions of this theorem. When it's going to be isomorphic to a product cobordism. And this proof, basically, I mean, it's due to Smale. It used Morse theory, I would argue, used Handel decompositions and used certain modifications of that. I don't want to go into the details, but let's say it's a worthy problem, and Serf wanted to, let's say, know himself better, develop the techniques a little bit further, to get a more structural understanding of Morse theory, to apply it to a little bit more general problem. Okay, and so the main sources, if you're interested in reading about this, there is an article by Serf himself, which is unfortunately only there in French. There is a follow-up article by Hedger and Wegener. Yeah, those are great sources to read about it. So the basic problem that one wants to attack while studying the structure of the space of Morse functions is that if you're unlucky, you can pick a very bad Morse function. It can have very many critical points that are in some sense unnecessary, and computations, like explicit computations, can become confusing or complicated. So what we want to do is that we want to kind of like optimize a Morse function, which now means that we want to cancel certain pairs of critical points, which we cannot always do. It depends on a certain condition with the existence of gradient flow lines between them. But basically what we want to do is the following situation. Here we have two extrema, a maximum and a minimum, two critical points. There is a unique gradient flow line between them, and we can continuously kind of like remove this pair of critical points. But we have a problem, we have some degenerate point in the middle. And degeneracies are not good for Morse functions. But anyway, that's what we have to live with. And so in order to get these cancellations and to study what they look like, Serf proposed stratification of the space of smooth functions on a manifold, which is defined by some notion of codimension of the function. And the codimension is defined in turn as the sum of codimensions of critical points and codimensions of critical values. And the codimension of a critical value is easy. You look at the pre-image, look at like how many critical points are in the pre-image, and you basically count them. And for the codimension of a critical point, you basically look at it somehow is this point in some sense degenerate, and there is some kind of way to measure how degenerate it is. If you want details, you take the ring of germs of functions that vanish at this specific critical point. You take inside that the ideal of that's generated by the partial derivatives of our function. And then you take the codimension as a vector space over the ring of real functions. And that turns out to be a finite number. If your point is non-degenerate, it's going to be 0. Yeah, and if it is degenerate, then it kind of like measures how degenerate it is. Okay, so what can the stratification do? It has the following properties. Generic Morse functions, so Morse functions for which all critical points have distinct values. They live in the zeroth stratum. Functions in higher strata either have higher order degeneracies or have critical values with multiple critical points in their pre-image. And any two Morse functions can be connected by a path that only crosses the first stratum in isolated points and otherwise is contained in the zero stratum. And actually, if such a path of function crosses the first stratum, then it means that, so it does that only in isolated points. So there is an isolated point where this function then may have a degenerate critical point, but a mild one. And otherwise, it's just going to be Morse functions. So yeah, the best kind of thing that we could hope to get. And functions in the same connected component of the space of Morse functions have the same number of critical points of the same index. Okay, and there is a nice graphical description of these kind of paths. There are these so-called Cerf diagrams. So basically, this would be such a cancellation of a critical point as I've shown them before. We have some function value of a critical point. We have some other critical value. We kind of move them together by perturbing the functions a little bit. And then at some point, when they become the same, then we have this degeneracy. And then afterwards, we remove the degeneracy. And yeah, we have a Morse function that does not have these two critical points anymore. And yeah, how does one prove this? I do not really want to go into the details. Let's say the only details I found were in the articles by Cerf. Like the English articles were like a little bit less on the details. And so these French articles involved a lot of analysis, I would say, this notion of universal unfoldings. You really have to analyze, okay, how do degenerate points or also like these birth and death points of pairs of critical points, how do they look like in local coordinates? How does a path look like that goes through such a degeneracy? And yeah, I would argue that it's a lot of work and non-trivial. And we're going to see in a couple of minutes that in the discrete case, it's a lot easier. Okay. So actually, this Cerf theory is very much related to discrete Morse theory, because that's kind of like what motivated Robin Foreman in order to come up with the discrete Morse theory. So in his first article on the subject, he even says that discrete Morse theory allows for an easier proof for the S-cobordism theorem, so the one with simple homotopy equivalences in the piecewise linear category. To the extent of my knowledge, I have not found a write-up of this proof in the literature. So for now, I guess we have to trust him on this. But anyway, so the idea is to perform these cancellations and modifications that that Smale did with the handle buddies, that we can do these directly on some combinatorial decomposition of our manifold. So we already start with a CW complex that we get out of a Morse function on the manifold, and do not need to care about smoothness or anything like this anymore, and can translate everything to combinatorics. Okay, how do we do that? So first of all, we need the notion of regularity. So a CW complex is called regular if all of the gluing maps are homeomorphisms. And as an additional definition, if I want to know if some cell is regular, then I want that the inclusion into a higher cell, so then it's a regular phase of the higher cell, if that is a topological embedding. Okay, and favorite examples of regular CW complexes are simplicial and cubical complexes. These show up a lot in topological data analysis, so we'll see that in a little bit, that will be interesting to us. And another notion I want to mention is the phase pose set that we have of any CW complex. So it has as elements just the cells of my complex. And whenever I have a phase of another cell such that there's no third cell in between, then I have a direct, like I have a what's called a cover relation. So in my phase pose set, it's lesser or equal to the other one, and there's none in between. And then I can depict this phase pose set as a directed graph like this, where I choose the convention that the arrows always go from the co-phase to the phase. So these two up here are the two cells, the ones in the middle are the one cells, and the one at the bottom are the zero cells. Yeah, and these phase relations are basically given by these gluing maps. And okay, why are phase pose sets convenient for discrete Morse theory? Well, or regular CW complexes rather. Well, if two regular CW complexes have isomorphic phase pose sets, then they are already homomorphic. So I can basically, for most practical purposes, study the topology of my CW complex just by studying the phase pose set, which is nice and combinatorial, and yeah, that's easier for me. All right, so what's a discrete Morse function? Well, the definition basically has three parts. So, or let's say four parts. First of all, it's actually a function defined on the phase pose set of the real numbers. And for every cell sigma, we have two conditions. So there can be at most one phase of sigma of codimension 1 that's gets a greater or equal function value. There can be at most one co-phase of codimension 1 that gets a smaller or equal value. And if some phase relation is not regular, then the function needs to be strictly increasing with respect to the phase relation. Okay, so this is a non-example because this one cell has a higher value than both of its co-phases. If we change it like this, then it is an example, and that's actually a class of examples already. So if we take any CW complex and we take the dimension function, then it's always going to be a discrete Morse function, a pretty boring one as we are going to see. This is also a discrete Morse function, which is, as we are going to see, a little bit more interesting. And there's a lemma by Foreman that for any cell sigma, there can only be one cell as in condition 1 or as in condition 2. There can be, there cannot be like a phase with a greater or equal value, or a co-phase with smaller or equal value at the same time. Otherwise, the condition of being a discrete Morse function is going to be violated on some other phase in between. Okay, and this fact that these times when, like in these conditions, I actually have an equal to 1 and not a less or equal to 1. So if such a phase or co-phase actually exists, the cells that create something like this kind of come in pairs. So this gives me a matching on my cells of my CW complex. And we denote these matchings by arrows, which point always in towards the higher dimensional cell. And this we call the combinatorial gradient field of our discrete Morse function. Okay, then it's a proposition or small theorem that these combinatorial gradient fields are in one-to-one correspondence with acyclic matchings on phase pose sets. So whenever I have some matching on my phase pose set, such that if I invert the arrows, I still, so I invert the arrows that belong to the matching, I still do not get any directed cycles. Then I can also get a discrete Morse function that induces this matching. And the path in this modified Hasse diagram, or like modified diagram that shows the phase pose set, those directly correspond to what are called combinatorial gradient flow lines. Okay. And now you might ask, okay, why? Like, what's the good stuff about this theory? Well, these combinatorial gradient fields provide simple collapses. So in the first lecture today, we talked about these simple homotopy equivalences. And whenever I have a matched pair here, then it actually turns out that the lower dimensional partner of the pair is in some sublevel complex a free phase, and then I can collapse it towards the higher dimensional partner and remove both of them without changing the homotopy type of my space. Of course, this changes the attaching maps of the higher dimensional cells potentially. So in this example, this Morse function that we had describe a collapsing down to a CW decomposition just with one 0 cell and one 2 cell. And here we see, well, it's not a regular CW decomposition anymore. So the phase pose set does not represent the topology anymore. Yeah, it does not represent the homotopy type even anymore. Okay. And then there is a nice scheme which is called cancellation of critical cells. And if you hear the name cancellation, you may recall that we had a similar notion in the smooth case, and we will see in a bit that it's actually the same notion. So whenever I have a discrete Morse function like this, I can pick unique gradient flow lines between pairs of critical cells. I mean, right now everything is critical, but if I just pick a gradient flow line, which is just some one simplex pointing to some zero simplex, then I can invert this. So I can match this one with this guy and get a way to collapse this. I can keep doing it with the easy ones as long as possible. And now I have this critical cell, this critical simplex in the middle left, and I have 4 critical 0 cells left, which I would kind of like to remove as much as possible. So I can just pick one gradient flow line, which goes from this one simplex to this thing labeled 3, to this thing labeled 9, to the thing labeled 1. I can invert it. And now I have an acyclic matching, which collapses even more. And now what we would like to do in discrete Morse theory is to perform such cancellations as much as possible in order to just simplify our space. Okay. Yeah, so here's a small dictionary between smooth and discrete Morse theory. So all of the notions translate to each other directly. And yeah, in the interest of time, I will skip over this, but any function on the phase pose set gives me sublevel complex filtrations, so do discrete Morse functions. How do they show up in topological data analysis? Well, it's called data analysis, so we start with some data. Then in topological data analysis, we want to have some combinatorial model for our data. Most times it's going to be some cubical or simplicial complex. What one would naively like to do is just compute topological invariants and use them to analyze data. The problem is that these don't usually, there is no canonical representation of our data set usually. And then the usual topological invariants do not behave well with respect to statistical analysis. So what we do instead is that we want to have filtered complexes. There are various ways to get them. And these filtered complexes can be interpreted as discrete Morse functions on certain spaces. So if we now want to do any later topological computation, like of any invariance, then it's useful to simplify these complexes before doing them. Because, I don't want to get into runtimes too much, but every step in this diagram has a kind of not ideal runtime. So simplification is really useful in order to actually be able to compute stuff. All right, so now we get to the space of discrete Morse functions. So if we have any finite CW complex, we can first start with the space of discrete functions, which is basically just a vector space generated by all our cells in our complex. And then there are 2 kind of canonical hyperplane arrangements in this space. One, which I call the symmetric arrangement, where I just take hyperplanes that are defined by like any equality of coordinates. And then there's a Morse arrangement, which is just generated by these cover relations, by these phase relations where there's no other cell in between. And this Morse arrangement has an orientation. So there is a positive side whenever the higher dimensional cell has a higher value. There is a negative side whenever the lower dimensional cell has a higher value. And then there is a side, like there's a hyperplane itself where both of them have the same value. And on the positive side, the pairs of cells are not matched by the Morse function. On the negative side or on the hyperplane, they would be matched. And so then not all intersections of hyperplanes are going to give us Morse functions. But it turns out that for any region of this hyperplane arrangement, like interior of the region, either all of the functions are discrete Morse functions or none of them. And all of these discrete Morse functions of the same region are going to give us the same combinatorial gradient field. So the same simple collapse or the same simple homotopy equivalence, if you like, that it defines. And yeah, here we have the easiest example. So we just take one simplex, because this one we can still draw. So I mean, a priori, it would be a three-dimensional space, but the line generated by 1, 1, 1 is always going to be like orthogonal to anything that's going to happen. So we can look at the orthogonal complement, and there we can see everything. So we have the critical region where there are all critical discrete Morse functions. There we also have the dimension function. Then we have one region where alpha and gamma, beta and gamma are matched here, alpha and gamma are matched here. And on this side, there are no discrete Morse function because then gamma has a smaller value than alpha and beta. Okay. And it turns out that this space of discrete Morse functions is actually contractible. So it's indeed star-shaped with the dimension function as a star point. So you can just calculate that any line between any discrete Morse function and the dimension function is contained in the space of discrete Morse functions. And then you can ask yourself, okay, what in like more generality do these functions look like? And then, I mean, it's quite easy, right? I mean, we have convex subsets of R to the n. We have some hyperplanes. So whatever path of discrete Morse functions we look like, it's either like some segment is contained in a region which contains discrete Morse functions. Then it may move through some hyperplane or through some intersection of hyperplanes, and then it might move into a different region. So it's basically the same story as in Cerf theory all along. And if it goes through some intersection where there's no discrete Morse function, then we can perturb it slightly. So it goes through some neighboring hyperplane, or it goes through a collection of hyperplanes. I mean, the space is star-shaped, so basically we can get the same kind of behavior as in the smooth case again. Yeah, I already said all of these points. And these degeneracies that showed up, I mean, there are two kinds of degeneracies that can show up. The one kind was going through like intersections of hyperplanes. I just explained how we can remove them. And then there is a different type of degeneracy that only exists in the smooth case due to the thing being smooth. So kind of like these other critical points of higher degeneracy, we just don't see them because the Morse theory just directly gets the matching when going through the hyperplane. So it becomes a little bit easier. Okay, so how is this related to smooth Cerf theory? Well, there's actually a theorem, and now you can take a guess who did all the heavy lifting for this theorem. That's right, Jean Cerf did it. Because already in 1970, more than 20 years before discrete Morse theory was invented, he basically wrote down the comparison map. So he said, if you pick some smooth Morse function, generic one maybe, there is some neighborhood such that there is a CW complex, which is going to be the CW complex induced by that Morse function or all of those Morse functions in this neighborhood. There are some stability results that guarantee that if you, I mean, I would need to make some more technical assumptions, but if you take those, then you get the same CW decomposition up to some notion called cell equivalence. And then you get a topological submersion of stratified spaces to some vector space, which is basically the space of discrete functions, together with the symmetric hyperplane arrangement. And it turns out that this map actually maps into the space of discrete Morse functions. It even maps into the critical chamber of this space. Okay, and then, yeah, sorry for all the text, but basically all of this says that if you have two smooth, okay, now here I put this, the technical conditions. So if you take Morse-Smale functions that arise from a cancellation of a pair of critical points, then the induced CW decompositions are simply homotopy equivalent by a simple collapse or a simple extension in the other way around. And the induced map on the space of discrete Morse functions is actually compatible with the Morse arrangements. And so you get an induced map between the spaces of discrete Morse functions. All right, and that's everything I wanted to say. So thank you for your attention.
Do we have any question? Bring you the microphone.
Okay. Well, yeah. I didn't. I think I slightly lost the analogy because, like, the space of, you said the space of discrete Morse functions is contractible, but the space of smooth Morse functions on a manifold is not contractible because you have to pass through the.
That's right. So the
fluctuation.
problem I have a little bit is that if I want to go from the space of smooth Morse functions to the space of discrete Morse functions, right now I can only do this like for a specific path component of the space of Morse-Smale functions. Otherwise, I get different CW decompositions. I mean, they're related to one another, but they're like, I mean, okay, I could try to define like a global space of all of discrete Morse functions that could come from smooth Morse theory. But the problem is a little bit that, okay, on which complex would this space live? So kind of like, I could draw an infinitely big diagram where I have like all of the different CW decompositions of my manifold that come from any Morse function. I have maps between those, and then I would need to take some big colimit of this infinitely big diagram, and then on that guy I would have the space of all of discrete Morse functions on this simple homotopy type, I guess. But yeah, so it's like I'm only taking some connected component of my space of like of the zero stratum.
And then that is contractible.
I think so, yeah.
Okay. Thanks.
Cool.
Other questions? If not, let's thank our speaker again. So now we have Tommaso Rossi that from the Università di Bologna that will talk us about the homology of the braid group over Z of the braid group.
Center.
The center.
The center.
Thank you.
Okay, thank you, and thank you for giving me this opportunity and for organizing this conference. And so today I'm going to talk about computation and group homology, and in particular I will compute the homology of a quotient of the braid group that we already saw before, but in order to fix some notation, I'm going to introduce it very briefly. So for me, Fn of C denotes the ordered configuration space, so the space of points inside C to the n that are distinct to each other. So this is the ordered configuration space. And you can think a typical element of this space will be a configuration of particles. Each one is now has a label by 1 to the n. Let's say, for example, this is for n equal to 3, and these particles are distinct. So now you can see that this space has an action of the symmetric group on n letters that permutes the labeling. So you can also consider the unordered configuration space, which is just the quotient of this by the symmetric group action. And today we will be concerned mostly about this guy here. So a typical element here is a configuration of distinct particles, but now you don't have labels. So all the points are equal. You cannot distinguish them. A nice feature of these spaces is that they are so fact. They are K pi 1 spaces in the sense that they do not have any homotopy group except for the fundamental group. And the fundamental groups of these spaces are well studied. In particular, the braid group is defined as the fundamental group of the unordered configuration space. So at least a part of the title is now clear to everyone. And let me just draw some pictures in order to understand why this is called the braid group. So, for example, take this configuration as the base point in, for example, C4 of C. And let's figure it out what a loop looks like in this space. So, for example, I can take the first 2 points and move them in a half circle. So I'm just moving them like this. This is a closed loop because the points are not numbered. And you can also picture this loop in the following way. So suppose here is the picture at time 0. And now on the vertical direction, there is the flowing of time. At time 1, you have the same configuration of points, since this is a loop. And the trajectories of the points are the following. The third and fourth point stay in the same position. So I draw the trajectories are just straight lines. While here you have this twist. So the trajectories are the following. And so now you understand why we call it the braid group, because we can picture this the element of this group like braids. Okay. Let me recall some basic facts about the braid groups. So we saw before a presentation of the braid group due to Artin, and I'm not going to recall it because it is not really important for this talk, but if you like a presentation of groups, you have a nice presentation for these groups. Another important fact is due to Fred Cohen, who computed basically the homology of Bn with integers coefficients, which since basically this is a model for the classifying space of the braid group, you can identify, if you are not comfortable with group homology, you can just think about the homology of the configuration space, because these two guys are the same. So this is computed. And I'm not going to tell you really what the answer look like, but let me remind you that if you take rational coefficients, the situation is very easy because you have only a class in degree 0 and a class in degree 1. While if you take integral coefficients, there are a lot of torsion classes that appears. So the answer is explicit but complicated. Okay, what I want to do today is to compute the homology of a quotient of the braid group. And so let me remind you what is the center of the braid group, which is well understood. So the center of the braid group is known to be a cyclic group of infinite order and is generated by a braid, which is usually denoted by delta squared. And delta here is the following braid. So imagine that you have your points in your configuration and you do a half twist. So you twist it by a half rotation. For example, if you have 4 points, no, let's see, 3 points, the center delta is the following braid. So the first point goes here, then you have this twist, and then this. And the center will be generated by this braid done twice. And it's a fine exercise to verify that the generators of the braid group commute with this braid squared. Okay, so the goal is to compute the homology of the braid group modulo the center, which from now on I just denote it by the integers because it's a copy of the integers, with coefficients in a field with p elements, so where p is a prime. So compute this for every n and for every p prime. And as in the case of the braid groups, if you take rational coefficients, the answer is very easy. Basically, you have the same homology of a point, so you don't have anything. All the homology is torsion. All the classes are of torsion classes. Okay, so to do this computation, usually if you want to do any computation in group homology, it's usually very useful to have a geometric model for the classifying space of your group. As for the braid group, you have a very nice geometric model for the classifying space, which is the configuration space. So let's try to figure it out, what should be the classifying space of this group. And to understand it, first note a very easy observation is that this group fits in a short exact sequence. So you have the center inside the braid group, and then you have the quotient. So this is an exact sequence. And what is the analogous of this sequence topologically? Let's try to figure it out. Let's apply the classifying space functor to each element of this sequence. What you get is that, in general, when you have an exact sequence, you will get a fiber sequence in topology. So you get a fiber sequence. And here you should have classifying space of the integers to the classifying space of Bn to the classifying space of Bn mod z. And now the classifying space of the integers is the circle up to homotopy. So this is the circle. The classifying space of the braid group, as we said before, is just the configuration space. So one is, in order to complete this with some space such that this is a fiber sequence, one first guess is to put here just the quotient by the circle action, because if you have any configuration, you can always rotate it by some angle. So you have an action of the circle here. So this, however, is not quite true, because basically this circle action is not free. And so when you take the quotient, you don't get a fiber bundle. So remark, this action is not free. For example, if you take a very symmetric configuration like this, okay, this is the origin, you should, this configuration is fixed by Z mod 3, seen as a subgroup, the subgroup of roots of unity. So this is not really a fiber sequence. It becomes a fiber sequence if I take the homotopy version of the quotient, which I'm not going to define, but I'm going to state a few properties so that if you never saw before this object, maybe you are more comfortable. Okay, maybe. Okay, so what do you have to know about homotopy quotient is that every time you have a group acting on a space, the notion of quotient is not homotopy invariant. For example, just take a point which is homotopy equivalent to a line. Here you have the trivial action of the integers because you have just a point. Here you have the action of the integers by translations. So these two guys are homotopy equivalent, and the homotopy equivalence is also equivariant respect to these actions. But if you take the quotients, you don't get homotopy equivalent spaces. Because on the one end, you get just a point. On the other end, you get a circle. So there is a construction in homotopy theory which fixes this problem. And all you need to know is that there is this construction such that if you have two homotopy equivalent spaces and the homotopy equivalence is G equivariant, then also the homotopy quotient are homotopy equivalent. And if the action is good enough, so if G acts on X freely, then you recover the homotopy quotient is up to homotopy the same as the ordinary quotient. So it's kind of a derived version of the ordinary quotient. Okay, so the upshot of this discussion is that now we have a nice geometric model for the classifying space of our group. And so to compute the homology, we only have to compute the homology of this space. So the upshot is that we have to compute the homology of a homotopy quotient. And for computing the homology of a homotopy quotient, there are a lot of techniques from equivariant homology. And in particular, the main tool to do this computation is to look, so the tool is to look at the Serre spectral sequence associated to the vibration Cn of C, Cn of C homotopy quotient S1, and the base is just the classifying space of the circle, which is the infinite projective space, so something that we know very well. Okay, so let me state the main result. Of course, if something is not clear, just interrupt me and ask a question. Okay. So, okay, so the good thing is that we have now many tools from this theory in algebraic topology, which is equivariant homology, to compute the homology of homotopy quotients. This is a general thing. And the results are the following. Or maybe I will just, before writing the results, let me write the spectral sequence. So in the second page, you have the homology of the configuration space, which is known by the work of Cohen, tensor the homology of the infinite projective space, which is known, and this converges to the homology of what we want to compute. And usually, the hard thing to do with spectral sequence is to prove that they degenerate. So when you want to do a computation, you usually hope that there are no many differentials and your spectral sequence stabilize quickly. So let's see the results. So if P divides the number of points or the number of points minus 1, then the homology of the braid group modulo the center with Fp coefficients is just isomorphic to the homology of the configuration space, tensor the homology of the infinite projective space. So in this case, the spectral sequence degenerates at the second page. So there are no non-zero differentials. Otherwise, there are a lot of non-trivial differentials, but there are a lot. So you have the degeneration, but at page 3. So otherwise, basically the homology of Bn mod z is equal to an explicit quotient of the homology of the configuration space. So in this case, basically in the third page of the spectral sequence, you only have the first column and all zeros. So here you have the degeneration, but at page 3. Okay, and one last thing, last result, is that in the same paper there is also another computation. So the computation of the homology of the braid group modulo the center, but with twisted coefficients. So this is the sign representation of sigma n, which is also a representation of the braid group, since this you have a map from Bn mod z to the symmetric group. So in the paper you find all this computation, but this computation is very different from these other ones. So here we use a spectral sequence and basic tools from equivariant homology, while in this other case there are completely different techniques. So let me conclude by explaining what tools you can use to prove the degeneration of a spectral sequence like this, because maybe it's useful for you to know. Okay, so I will delete maybe. So the main tool is a very general theorem which you can find in classical textbook about equivariant homology. So suppose you have a space with an action of the circle and you want to consider the Serre spectral sequence associated to the vibration x to x mod s1 to bs1. And you do it with coefficients in a field of prime with p elements. Then you have a very powerful result which tells you the following. So if some conditions hold, so So let me explain this formula. Of course, if you have a disequality, so you compute the Betti numbers with the mod p coefficients of your space, and you sum it. And of course, here you have to assume that this sum is finite. And you find out that this sum is equal to the sum of the Betti numbers of the fixed point locus. So these are fixed points respect to Z mod P, which is seen as a subgroup of the circle, the subgroup of roots of unity. So if you have this equality of numbers, then you can conclude that your spectral sequence associated to this vibration degenerates at the second page. So you don't have any differentials. In my case, okay, X was the configuration space. So my X was the configuration space. So this term, you can compute this term thanks to the work of Fred Cohen, because the homology of configuration spaces is well known. So the only thing I have to do is to understand the fixed point locus. And let me just sketch geometrically what it looks like. So, okay. Basically, the real reason, because you have these two very different behaviors, depending on the divisibility of n mod p or not, is that basically if p divides n, then the fixed points is homomorphic to a configuration with n mod p points in the plane with a hole. If p divides n minus 1, you have a similar thing. So Cn of c z mod p is equal to Cn minus 1 mod p c in C star. Otherwise, you have the empty set. So you don't have any configuration which is symmetric respect to this subgroup. And this is the real reason, because on the one hand, you don't have differentials, and on the other hand, you have many differentials. And the geometric reason for this homomorphism is that, for example, take p equals to 3, and you want to understand the configurations which are symmetric respect to the rotation of Z mod 3. And so if you divide the plane in 3 equal regions, if you put some point here, since the configuration must be symmetric, you should have the same point here, the same point here, and so on. So everything you put here, you should put the same thing here and the same thing here. So here, the only thing you have, if p divides n, you put n mod p points in this region, and the same configuration here and the same configuration here. And then you observe that if some point approaches this line, so basically a configuration symmetric with this symmetry is determined by what you put in this region. So maybe in this region. And then you observe that if a particle approaches this line, you will have the same basically picture in all the other regions. And when it crosses it, you will see it reappear from the other side. So you should glue these two lines together. So you get a configuration with n minus p points in the plane, but minus a point, because you cannot put any point in the center if n is divisible by p, because if some point approaches the origin, then you will have a collision of 3 points, which is not allowed in the configuration space. And similarly, you can do for this guy. Okay, I think it's fair if I and a few minutes before because I'm the last. So thank you for your attention.
Okay. Thank you, Tommaso. Does anybody have any question? Okay, I hand you the microphone.
So I actually have two questions. So the first one is, okay, so you have those observations that the fixed points are another configuration space in a different space. That would imply, I assume, that the dimensions fit
Yes,
in this way.
it's not, I mean, it's the content of this paper to show this bijection, this equality. It's
Right.
not
Because you know the homology of the various configuration spaces.
yes. Okay, that's something that I would have to point out, that this guy is really similar to this, and the homology of these guys is implicit in the work of Fred Cohen too. So in the work of Fred Cohen about iterated loop spaces, there are a lot of computation about configuration spaces, and so also the homology of this guy here is computed, and so you can check this equality.
Okay, thank you. And the second question I have is about the third part, not the third, the second part of your theorem, that the second.
Okay.
So that the specular sequence collapses at E3, and you have everything in the fiber line. So I'm wondering how that happens.
Just an explicit computation, because in the second page you can the differential is quite explicit because you can prove that it is induced by the circle action. So if you know the circle action on the homology of the configuration space, you can compute explicitly the differentials on an additive basis, and then you see that there are a lot of classes that if they are cycles, they are also boundaries of something, and so basically you just check that except for the first column, you don't have homology.
Right. So everything is basically the same except for the fiber line.
Yeah, because in the first line you have zero differentials, so
Right,
all the things are cycles.
Thank you.
I go.
Okay, my question is also about the second line of your result. How explicit is that quotient?
Explicit in the sense that for a specific n and a specific p, I can tell you an additive basis.
Okay, so you know the dimension
Yeah.
of that thing. There is a closed formula for it.
Yeah, if you write down explicitly the homology of configuration space, I can tell you, okay, you have a basis of the homology of the configuration space, and I can tell you this guy is also a basis element of it or not. So
Okay,
it's quite explicit.
Thank
you.
Yeah. Wait, I have another one first.
I had the same. I was just going to ask.
Okay.
So since you're working with FP coefficients, you can actually dualize and go for cohomology. So instead of co-kernel, you're going to have kernels, and then can you compute the multiplicative structure?
At least I was not able to compute the multiplicative structures because there were some non-trivial extension problems that I was not able to solve. In what cases? In this case or
Second case.
Okay, I show you with an example maybe, because if you take p equals to 2 and configuration space of 2 points in C, which is the classifying space of the braid group with 2 strands, which is the integers. The homotopy quotient is a classifying space for Z mod 2. So is a copy of the real projective plane. And in the spectral sequence, you have like a class. In the fiber, you have only 2 classes because this is a circle. right? And then and so on. And now, what was the problem? Okay, I think that here okay, maybe I should think about a bit more this example, but at the time I was not able to find the multiplicative structure, and now I don't remember why. Oh, okay, maybe I should ask you how to do it, because it will be interesting.
Okay. So maybe for today we are done. We thank Tommaso again.